Science. 18. Energy. The science of energy, harnessing power for the modern world. The law of conservation of energy. The law of conservation of energy is a fundamental principle in physics that states that energy cannot be created or destroyed, only transformed from one form to another. This principle provides the foundation for all energy studies and technologies. It means that the total amount of energy in a closed system remains constant over time. This concept is crucial in understanding the various energy transformations that occur in our daily lives, from the conversion of chemical energy in food to the mechanical energy used for physical work. The law of conservation of energy serves as a guiding principle in the development of sustainable energy systems, as it emphasizes the importance of efficient energy use and the need to minimize energy losses. Fossil fuels. Fossil fuels, such as coal, oil, and natural gas, have been the dominant energy sources for human civilization for centuries. These fuels are formed from the remains of ancient plants and animals that were buried and subjected to high pressure and temperature over millions of years. Fossil fuels provide a concentrated source of energy and have been crucial for powering industrialization, transportation, and electricity generation. However, their extensive use has led to significant environmental challenges, including air pollution, greenhouse gas emissions, and climate change. As we transition to more sustainable energy sources, reducing our dependence on fossil fuels and finding alternative solutions will be essential for mitigating the environmental impact of our energy consumption. Renewable energy. Renewable energy technologies, such as solar, wind, and hydroelectric power, harness natural processes that are replenished over time to generate sustainable and clean energy. Solar energy utilizes the sun's radiation, while wind energy converts the kinetic energy of the wind into electricity. Hydroelectric power harnesses the gravitational potential energy of water flowing from higher to lower elevations. These renewable energy sources offer significant advantages, including reduced greenhouse gas emissions, improved air quality, and decreased reliance on finite resources. The development and deployment of renewable energy technologies are crucial for transitioning to a low-carbon and sustainable energy system, contributing to global efforts to mitigate climate change and ensure a secure and resilient energy future. Nuclear energy. Nuclear energy is derived from nuclear reactions, specifically the process of nuclear fission, which involves the splitting of atomic nuclei. Nuclear power plants use controlled nuclear reactions to generate heat, which is then converted into electricity. Nuclear energy provides a significant portion of the world's electricity, offering a reliable and low-carbon energy source. It has the advantage of producing a large amount of energy from a relatively small amount of fuel and has a lower greenhouse gas emissions profile compared to fossil fuels. However, nuclear energy also poses challenges, including the management of radioactive waste and the potential risks associated with accidents or nuclear proliferation. Ongoing research and technological advancements are focused on improving the safety, efficiency, and sustainability of nuclear energy. Energy efficiency. Energy efficiency refers to the optimization of energy use and the reduction of energy waste in various systems and processes. It involves implementing technologies, practices, and policies that maximize the output or benefits obtained from a given amount of energy input. Energy efficiency measures can be applied in buildings, transportation, industrial processes, and appliances. By improving energy efficiency, we can reduce energy consumption, lower greenhouse gas emissions, and decrease the overall demand for energy resources. Energy-efficient technologies, such as LED lighting, smart thermostats, and energy-efficient appliances, play a crucial role in achieving sustainability goals and transitioning to a more energy-efficient future. 6. Electricity generation and distribution. Electricity generation is the process of converting various energy sources, such as fossil fuels, nuclear energy, and renewable sources, into electrical energy. This energy is then distributed through power grids to homes, businesses, and industries for use. The generation and distribution of electricity involve complex systems and infrastructure, including power plants, transformers, transmission lines, and distribution networks. Advances in electricity generation technologies, such as combined cycle gas turbines and renewable energy systems, have improved efficiency and reduced environmental impact. The development of smart grids, which utilize digital communication and advanced monitoring systems, enables more efficient and reliable electricity distribution, promoting energy conservation and facilitating the integration of renewable energy sources. 7. Thermodynamics. Thermodynamics is the branch of science that deals with the relationship between heat, work, energy, and temperature. It provides the foundational principles for understanding and designing energy systems, from engines to refrigerators. The laws of thermodynamics, including the conservation of energy, entropy, and the transfer of heat, govern the behavior of energy and its transformations. Understanding thermodynamics is essential for optimizing energy conversion processes and increasing efficiency. It plays a crucial role in the design of power plants, the development of energy storage systems, and the study of energy flow in natural systems. Thermodynamics provides the framework for analyzing and improving the performance of energy systems while considering the limitations imposed by the laws of physics. 8. Energy storage. Energy storage technologies play a critical role in capturing and storing energy for later use. With the increasing integration of intermittent renewable energy sources into the grid, energy storage becomes crucial for balancing supply and demand and ensuring grid stability. Various energy storage methods exist, including batteries, pumped hydro storage, compressed air energy storage, and thermal storage. Advances in battery technologies, such as lithium-ion batteries, have significantly improved energy storage capacity and efficiency. Energy storage systems enable the utilization of excess energy during periods of low demand and its release during peak demand, reducing the need for conventional power plants and enhancing the integration of renewable energy sources. Efficient and cost-effective energy storage is vital for enabling a reliable, flexible, and sustainable energy system. Bioenergy. Bioenergy refers to the energy derived from biomass, which includes organic materials such as plants, agricultural residues, and wood. Biomass can be converted into various forms of energy, including heat, electricity, and biofuels. Bioenergy technologies, such as biomass combustion, anaerobic digestion, and bioethanol production, provide a renewable energy source that can replace fossil fuels in sectors such as heating, transportation, and electricity generation. The use of bioenergy offers the advantage of utilizing organic waste materials and reducing greenhouse gas emissions compared to fossil fuels. However, sustainable bioenergy production requires careful consideration of land use, biodiversity, and the potential competition with food production. Advances in bioenergy technologies focus on increasing efficiency, reducing environmental impacts, and exploring advanced biofuels made from non-food feedstocks or algae. 10. Geothermal energy. Geothermal energy harnesses the heat stored within the Earth's interior to generate electricity and provide heating and cooling for buildings. This renewable energy source utilizes the natural heat from the Earth's crust, typically accessed through geothermal power plants or geothermal heat pumps. Geothermal power plants convert the high-temperature geothermal fluid or steam into electricity, while geothermal heat pumps transfer heat between the ground and buildings for heating or cooling purposes. Geothermal energy is reliable, abundant, and produces low greenhouse gas emissions. It offers a stable energy source that is not dependent on weather conditions, making it an attractive option for regions with geothermal resources. Continued research and development in geothermal technologies aim to improve efficiency, expand resource utilization, and enhance the sustainability of geothermal energy production. 11. Fuel cells. Fuel cells are devices that convert the chemical potential energy of a fuel, such as hydrogen, into electrical energy through an electrochemical reaction. They provide a clean and efficient method of producing electricity, with water and heat as the main byproducts. Fuel cells have a wide range of applications, from portable power systems to stationary power generation for buildings and vehicles. Hydrogen fuel cells, in particular, offer the potential for zero-emission transportation, as they produce electricity by combining hydrogen with oxygen from the air, resulting in water vapor as the only exhaust. The development of fuel cell technologies focuses on improving efficiency, durability, and affordability, as well as exploring alternative fuel sources beyond hydrogen, such as methanol and natural gas. 12. Energy transition. The energy transition refers to the global shift from a predominantly fossil fuel-based energy system to one that is more sustainable, low carbon, and based on renewable energy sources. The transition is driven by the need to address climate change, reduce greenhouse gas emissions, enhance energy security, and promote economic development. It involves a multidimensional transformation that encompasses technological advancements, policy frameworks, market dynamics, and societal change. The energy transition requires significant investments in renewable energy infrastructure, energy efficiency measures, and the development of supportive policies and regulations. It also involves fostering innovation, public engagement, and international cooperation. The energy transition is a critical pathway towards a more sustainable future, promoting a resilient, secure, and environmentally responsible energy system. 13. Smart grids. Smart grids are modern energy supply networks that integrate digital technology, advanced sensors, and communication systems to optimize the production, distribution, and consumption of electricity. These intelligent grids enable real-time monitoring, control, and management of energy flows, enhancing the reliability, efficiency, and resilience of power systems. Smart grids facilitate the integration of renewable energy sources, enable demand response programs, and provide consumers with more information and control over their energy consumption. They support the transition to a more decentralized and flexible energy system, with active involvement from consumers, distributed energy resources, and energy market participants. Smart grid technologies play a crucial role in balancing electricity supply and demand, reducing peak loads, and improving grid stability, ultimately contributing to a sustainable and efficient energy infrastructure. 14. Carbon capture and storage. Carbon capture and storage, CCS, is a technology that aims to capture carbon dioxide, CO2, emissions from industrial processes or power generation and store it underground, preventing it from entering the atmosphere and contributing to climate change. CCS involves capturing CO2 from power plants or industrial facilities, compressing it into a dense form, and transporting it to suitable geological formations for long-term storage. This technology offers a way to reduce CO2 emissions from fossil fuel-based power generation and industrial processes, helping to mitigate climate change. It also has the potential for carbon dioxide utilization, where captured CO2 can be converted into valuable products. Research and development efforts in CCS focus on improving capture efficiency, reducing costs, and identifying suitable storage sites while ensuring the safe and permanent storage of CO2. 15. Tidal and wave energy. Tidal and wave energy harness the power of the ocean's tides and waves to generate electricity. Tidal energy is derived from the gravitational pull of the moon and the sun, which creates the periodic rise and fall of tides. Tidal power plants utilize the kinetic energy of moving water during the ebb and flow of tides to drive turbines and generate electricity. Wave energy, on the other hand, captures the energy of ocean waves using devices that convert the up and down or back and forth motion of waves into electricity. Tidal and wave energy offer significant potential as renewable energy sources, as they are predictable and have high energy density. Ongoing research focuses on developing efficient and reliable technologies, optimizing device designs, and addressing environmental considerations for the deployment of tidal and wave energy systems. 16. Hydrogen energy. Hydrogen energy holds great promise as a clean and versatile energy carrier. It is the most abundant element in the universe and can be produced from various sources, including electrolysis of water using renewable electricity, natural gas reforming coupled with carbon capture and storage, and biomass gasification. Hydrogen can be used in fuel cells to generate electricity, burned as a fuel in internal combustion engines, or combined with other chemicals to produce synthetic fuels. Hydrogen energy offers the advantage of producing zero greenhouse gas emissions when used in fuel cells, with water as the only byproduct. It has the potential to decarbonize various sectors, including transportation, industry, and power generation. Research and development efforts focus on improving hydrogen production methods, storage technologies, and infrastructure to support the widespread adoption of hydrogen energy. 17. Energy policy. Energy policy encompasses the formulation and implementation of strategies, regulations, and measures that guide the development, distribution, and use of energy resources. Energy policies aim to ensure the availability, affordability, and sustainability of energy while addressing environmental concerns and promoting economic growth. They cover a wide range of areas, including energy efficiency, renewable energy incentives, emissions reduction targets, energy market regulation, and international cooperation. Effective energy policies provide a supportive framework for technological innovation, investment, and market competition, facilitating the transition to a more sustainable energy system. They also play a crucial role in shaping energy markets, influencing consumer behavior, and driving the adoption of clean and efficient energy technologies. 18. Energy and transportation. The transportation sector accounts for a significant portion of global energy consumption and greenhouse gas emissions. The transition to cleaner energy sources in transportation is crucial for reducing environmental impacts and achieving sustainable mobility. Electric vehicles, EVs, powered by electricity from renewable sources, offer a promising solution to decarbonize transportation. They produce zero tailpipe emissions and can contribute to overall emissions reduction when charged with clean energy. Additionally, biofuels derived from renewable resources, such as ethanol and biodiesel, provide an alternative to fossil fuels in conventional internal combustion engines. Sustainable transportation solutions also include improved public transportation systems, alternative fuel infrastructure, and promoting active transportation modes like cycling and walking. The adoption of clean and efficient energy technologies in transportation is key to achieving a more sustainable and low-carbon future. 19. Photovoltaics. Photovoltaics, PV, is a technology that converts sunlight directly into electricity using semiconductor materials. Solar cells, also known as photovoltaic cells, are the basic building blocks of PV systems. When sunlight strikes a solar cell, it creates an electric current due to the photovoltaic effect. PV systems can range from small-scale installations for residential use to large utility-scale solar power plants. Photovoltaics offer a clean and renewable energy solution, with solar energy being abundant and widely accessible. The declining costs of PV systems, along with technological advancements, have significantly increased their deployment and made solar energy competitive with traditional energy sources in many regions. Ongoing research focuses on improving PV efficiency, developing advanced materials, and integrating solar energy into the grid to enhance the reliability and scalability of solar power. 20. Energy and society. Understanding the societal and economic impacts of our energy choices is crucial for achieving a sustainable energy future. Energy decisions influence social equity, economic development, and environmental sustainability. Access to affordable and reliable energy services is essential for improving living standards, education, healthcare, and economic opportunities. Energy choices also affect energy security, energy affordability, and the resilience of communities. Energy literacy and public engagement are necessary to create an energy system that addresses the needs of communities. 21. Future of energy. Exploring potential future energy sources and technologies is essential for shaping our energy future. Advancements in science, engineering, and technology have the potential to revolutionize the way we generate, distribute, and use energy. Fusion power, for example, holds the promise of clean, abundant, and virtually limitless energy by replicating the processes that power the sun. Other emerging technologies, such as advanced energy storage systems, artificial photosynthesis, and carbon capture and utilization, offer potential solutions to current energy challenges. Additionally, integrating multiple energy sources, creating energy systems with enhanced resilience, and leveraging digital technologies to optimize energy use are areas of ongoing research and development. The future of energy will likely be characterized by increased decentralization, renewable energy integration, intelligent systems, and an emphasis on sustainability and environmental stewardship. Thanks for watching. Please like, share and subscribe, and comment below if you agree, or would like to add your thoughts.